In this lesson, we're going to talk about measurements and accuracy versus precision. We're going to touch on error and uncertainty and on how we deal with error and uncertainty in terms of our measurements and our calculations by using significant figures. So, first off, all good measurements must have both a number and a unit. Remember, we've talked about the unit is what gives a number meaning. Without a unit, numbers are meaningless. Now, when we make measurements, we want to strive for the best possible measurement we can make. So, we throw about these terms precision and accuracy a lot of times, and we think that they're the same thing, but really they are not. Precision refers to how close a group of measurements are to one another. And accuracy, or how accurate a measurement is, refers to how close it is to what the true value of whatever's being measured is. So, we oftentimes use this dartboard analogy. So, here we have all of our darts, the blue dots. They're all really close to the bullseye. So they're all really close to the bullseye. They're all really close together. We would say this has got a high precision and high accuracy. It's really close to the center. Now, on this middle one, we've got all the darts, all the blue dots are near each other. In this case, they're off to the edge. They're not at the bullseye. So we're not close to the true value. But we are close to each other. So we would say that these have precision but not accuracy. And then finally, we have a whole bunch of randomly scattered dots. So none of them are near the bullseye and none of them are near each other. So in this case, we have poor precision and poor accuracy. Now, precision also refers to how good a measurement is in terms of where is your last error digit. Okay? So the more digits that you can count in your measurement, the more precise your measurement is. And by a standard, we call the error or the uncertainty to be plus or minus 1 of whatever the last digit in the measurement is. So, for example, if I measured the volume of water 5.00 milliliters, so I measured to the 100th of a milliliter, the uncertainty in that measurement is plus or minus 0.01 milliliters, one of the last digit in the measurement. So we can actually mathematically show how good our measurements are and how precise our measurements are through the use of what are called significant figures, or as everybody affectionately calls them, sig figs. So sig figs. So what is this concept of the sig fig? These are all the numbers that need to be in a measurement. They tell us the precision of the instrument being used to measure. So when we make measurements, we need to make sure that we capture all of the numbers that are certain digits, and then we have to estimate our uncertain digits. So in the previous slide, if I measured 5.00 milliliters, the last digit, that second zero, is my estimated digit. That's where my uncertainty is. That's why we had the error defined as plus or minus 1 of that last digit. So these significant figures tell us how good a measurement is. They tell us how good the measuring device is. And they tell us everything we need to know about the measurement without having to tell us every single detail of the measuring device. And we want to make sure that when we make a measurement that they are good measurements, that we follow accuracy and precision as best as we can. Why? Well, imagine if you were on an airplane and the pilot said to you, well, our travel time is going to be 4 hours and 30 minutes. And you got there in 45 minutes. You would think that that pilot doesn't know what he's doing because he can't estimate how long you're going to be in the air. He has a lot of error associated with that. Or if your doctor prescribed medication, and let's say it was per kilogram body weight, so let's say 5 milligrams per kilogram body weight, if they didn't measure your body weight very accurately or very precisely, then you could get the wrong medication dosage, which could be potentially fatal. So significant figures are very, very important. Those are just two generalized ideas. One of the key things with significant figures is if you make measurements and you try to build something, the significant figures comes into the tolerance of something. So how tightly things are put together. If there's a lot of wiggle room in a device, it may fail. So for example, would you want somebody to build a roller coaster and only measure all of their measurements to, say, the nearest foot, so that when you go to put it all together, it's all wobbly and scary? No, you want to make sure that your measurements are as good as they can possibly be. We have some rules for determining the number of significant figures in a measurement. And to count the sig figs, this is actually pretty easy. So all you have to know are these rules. Anything that's not a zero is significant. Anything that's not zero is significant. That's pretty simple. So the measurement 1.234 kilograms has 1, 2, 3, 4 sig figs. So anything that's non-zero, always significant. Now, zeros are the only thing that's left over. We've talked about anything that's not a zero, so now we have to talk about zeros. Zeros come in 3 flavors. They come with captive zeros. Captive zeros are those zeros that fall between 2 non-zero digits. And these are always significant. So these zeros here fall between 2 non-zero digits. Therefore, those zeros are significant. So the 1, the 2, the 3, and the 4, the non-zero digits are significant. So there's 4 non-zeros, and those 2 zeros that are captive are significant for a total of 6 sig figs. The next type of zero is a leading zero. These come before a non-zero digit, and they are never significant. These are simply placeholders telling you how far you have to move the decimal place. So here we have 2 leading zeros. These are never significant. So this number has only these 4 non-zero digits. So we have 4 sig figs. And finally, trailing zeros. These zeros come at the end of a number and are significant if and only if there is a decimal point involved. So here we have a 0 and there is a decimal point. So that 0 is significant. So we have 1, 2, 3, 4, 5 sig figs. So let's count a few sig figs in a measurement. This first one, we have 1.2 millimeters. We've got 2 non-zero digits. There are no zeros, so this must have, that's right, 2 significant figures. What about 5.60 meters per second? Well, we've got 2 non-zero digits, so we know we've got at least 2 sig figs. And we've got a 0 that comes at the end of a number. That's a trailing 0. Now, what do we know about trailing zeros? They're significant if and only if there's a decimal point. Is there a decimal point? Yeah, so it's significant. So this one has 3 sig figs. 102 milliliters. We've got 2 non-zero digits, and we have a 0 that comes between 2 non-zero digits. That's a captive 0. Captive zeros are always significant, so we have 3 sig figs in 102 milliliters. Now what about 0.1230 centimeters? We've got 3 non-zero digits, and we've got 2 zeros, but they come in different spots. We have a 0 at the beginning of a number and the 0 at the end of a number. The beginning 0 is a leading 0, and leading zeros are never significant. They're simply placeholders. Then we have a trailing 0. Now that trailing 0, there's a decimal point involved, so that must be significant. So 0.1230 centimeters has 4 sig figs. 1.0200 megagrams, we've got 2 non-zero digits, a captive, and 2 trailing zeros. We also have a decimal point involved. So all of those zeros are significant. So we have a total of 5 sig figs. And finally, 1,300 kilograms. We've got 2 non-zero digits and we've got 2 trailing zeros. But those trailing zeros, there's not a decimal point there. So since there's no decimal point, they're not significant. So we only have two sig figs, the 1 and the 3. Now here's some reminders about sig figs. Significant figures only come from measurement. So they only are when you measure something. If you're counting something, counting is an infinite sig fig deal, okay? Because you're not measuring, you're counting. And defined numbers also are considered to have infinite significant figures. In other words, our powers of 10, our metric system. So 100 centimeters is equal to 1 meter. We call each of those as having infinite sig figs because it is a defined number. So counting and defined numbers have an infinite number of sig figs. Alright, so we've counted our sig figs, and that's pretty simple. We just got to remember when our zeros are significant. Now, when we're doing math with measurements, so when we're multiplying or adding or dividing or subtracting measurements, we need to make sure that we adhere to some certain rules so as not to understate or overstate how good our measurements are. So the math and sig figs, we have some definite rules. So let's say we were making a measurement on this balance, and we wanted to subtract out the mass of the flask holding the liquid. We have to make sure that we subtract the mass from the mass of the total liquid and glass, and do so that we preserve how good our balance measurements are. These balances are usually accurate and precise to the 4th decimal place. So how are we going to go about conserving that accuracy and precision? So multiplication and division with significant figures is actually the easier process. So if you're going to multiply or divide measurements, the total number of significant figures in your answer must be the same as the least number of significant figures in the operation. In other words, you count the number of sig figs in each measurement, and whatever one is the smallest is the number of significant figures you should have as an answer. So in this case, if I want to divide 2.50 centimeters by 1.2234 seconds, 2.50 centimeters is 3 sig figs, 1.2234 is 5 sig figs. My answer should have 3 sig figs, and that's it. Now, it's also very important that you remember your order of operations. Remember, please excuse my dear Aunt Sally, or PEMDAS. Please excuse my dear Aunt Sally. So parentheses, exponents, multiplication, division, addition, and subtraction. So addition and subtraction, when we do an addition or subtraction, what we're going to do is we're going to line them up, and we're going to take the least decimal place, and that is what's going to control our sig figs, which means we can add or subtract, or I shouldn't say add or subtract, but we can gain or lose significant figures based upon the addition and subtraction and where our decimal places are. So you can see here, if I have 2.53 centimeters plus 120.1 centimeters, if I just add that up, that comes out to be 122.63, but that's not following our significant figure rules. Nor do we want to cut it at 122 centimeters, 3 sig figs like our least measurement. That's not good enough either. But if I add that up, 2.53 plus 120.1, and cut it at the least decimal place, or at that tenths place, my answer is 122.6, because my least decimal place comes out of the 120.1. So remember, you can lose or gain the total number of significant figure in your answer. So here's the idea, is make sure you line it up like we did in grade school. This is the easiest way to ensure that you're going to get the right answer. So if I had 55.36 millimeters plus 100.6 millimeters, and I line that up, I'm going to cut my number off at the tenths place, so 155.9. Now, we have that 155.9, but the next number is a 6. So, just like we do in all of our other bits of math, we can round. Now, when we round that 6, what happens? Round up the 9 becomes a 10, so it becomes a 0, and then we add 1 to our ones place, and we end up with 156.0 millimeters. That is the number of significant figures we want, and that's the correct answer. So now we're going to attempt to do some problems dealing with the multiplication, division, addition, and subtraction of significant figures. So for the first one, let's add 135.6 plus 221.56 plus 312. Then we'll do 23.45 times 24.2, and then 3.6 divided by 2.1, and then we have a multiple step problem. We have 234 plus 3.2 times 6.54. So let's do these problems. So here I have the first two problems written. 135.6 plus 221.56 plus 312. Now, I've lined them up so that all the decimal points hit the same spot. So when we go ahead and add these up, we'll have a 6 there. 6 plus 5 is an 11. The decimal point goes there. We add 1 to our number, so that's 5 plus 6 plus 1. That's 7 plus 2 is 9. And 3 plus 2 is 5 plus 1 is 6. And then 1 plus 2 plus 3 is 6. So from straight addition, we see it's 669.16. But now, look, our least decimal spot is the ones place, because I'm going to run my number down there and keep all those digits there. So my answer should be 669. Now with 23.45 times 24.2, I don't have to line them up or anything. All I have to do is multiply. Now, 23.45 has got 4 significant figures. 24.2 has 3 significant figures, so I should only have 3 sig figs in my answer. And when I do the multiplication, what I get is 567.49. Now, I only want 3 sig figs, so I'm going to start counting here. So 1, 2, 3. Now, whenever I look at these, I need to actually go ahead and start determining whether I need to round. Now, the next digit, the digit that's going to start our dropped digits, is less than 5. So if it's less than 5, we don't round up. We keep the number the same. So my answer should be 567. Alright, for the next two problems, we've got 3.6 divided by 2.1, and then the slightly more complex 2.34 plus 3.2, all multiplied by 6.54. So 3.6 divided by 2.1. Both of them have 2 significant figures in the answer. Now if I put in my calculator 3.6 divided by 2.1, what do I get? So 3.6 divided by 2.1 is equal to 1.71. Now, I only need 2 significant figures, so I'm going to take a look. I've got 1, 2, and that next digit that's going to be dropped is less than 5, so I keep it as 1.7. Now in the second problem, 2.34 plus 3.2 times 6.54. It's not as easy as going, oh, it's this. What we need to do is we need to take a look at each portion of the order of operations. So remember, please excuse my dear Aunt Sally. The first thing we're going to do is we're going to do what's in parentheses. So we're going to take the 2.34 plus 3.2, and that gives us 5.54. Now we're going to take that number and multiply by the 6.54. And when I do that, what do I get? I get 36.2316. Now, that's way too many significant figures, but how many sig figs should I actually have? Well, now we have to take a look. When you do the calculations, you keep every number until the very end. At the end is when you determine your number of sig figs. So that's why we didn't bother cutting off the 5.54. But what happens if we do? So when we look at this and we cut down our significant figures, the order of operations in our parentheses, the 5.5, should only have 2 significant figures. So that 2 sig figs there times our 3 sig figs here means that our answer should only have 2 sig figs in it. So we would have 36. And that is the total number of sig figs we have, 2 sig figs, because of our order of operations. So whenever you're doing any calculations, you always carry through every number and only deal with determining the sig figs at the very end.